Okay, continuing our discussion of one-dimensional forces, let's take a look at number 4. How much tension must a cable withstand when used to accelerate a 1,350 kilogram car vertically at 0.85 meters per second squared? So we are looking for how much tension must a cable be able to withstand. So the force of tension, okay, is equal to what? Well, the force of tension is equal to the net force. So the net force that is acting on it minus the weight, or the force of gravity. Okay, so we're going to have to figure out the force of gravity and the net force in order to figure out what the tension is on the cable. And we need to know how much it must be able to withstand. Okay, so it's being used to accelerate a 1,350 kilogram car. So the mass is 1,350 kilograms. Okay, and the acceleration that it is accelerating at is 0.85 meters per second squared. So this right here, the combination of these two will give us the net force. We are also going to have to calculate the force of gravity. Okay, so let's start with the net force since it gave us that information. So my F net is equal to 1,350 kilograms times 0.85 meters per second squared. Okay, so my net force is equal to approximately 1,147.5 newtons. Okay, the force of gravity is equal to that same mass, so 1,350 kilograms times negative 9.8 meters per second squared. Okay, so which will give us a force of gravity, or a weight, of negative 13,230 newtons. So then my force of tension, like I said, the force of tension is the net force minus the force of gravity. So all I have to do then is plug in, I know, so the force of tension is equal to the net force, 1,147.5 newtons, minus negative 13,230 newtons. So if I do minus a negative is the same as adding those two together. So that is going to give me a total of 14,377 newtons. And I need to round this to two significant figures because that's all I have for my acceleration. My acceleration only has two significant figures. So I need to make sure that I have two significant figures. Now, here's where we have to be careful. It says that the cable must be able to withstand at least this amount. Okay, we don't want the cable to snap. So I can't round down, even though this is a lower number. Because of the problem itself, I have to round that to 15,000 newtons in this case, because I don't want the elevator cable to snap or whatever. Oh, it's a car, excuse me. I don't want the car to snap and then fall on somebody. So we need 15,000 newtons for our final answer. In other words, that's what the cable must be able to withstand. Okay, moving on to number 5, it says airbags are designed to protect passengers during collisions. Compare the force required to stop a 65 kilogram passenger in a car that is moving at a speed of 20 meters per second when a collision occurs. Okay, if the force is required to stop them in 0.75 seconds by a deployed airbag and what force is required to stop the same passenger in 0.025 seconds by the dashboard. Okay, so in other words, the airbag slows down the time that they have to stop, okay, versus the dashboard, because it has no cushion to it, that time is almost instantaneous. So how much force does the dashboard exert on the passenger versus how much force does the airbag exert on the passenger, because that time to stop them is increased. So we're going to see what that looks like here. So the first thing that we need to do is figure out what the acceleration is. Okay, we're given an initial velocity of 20 meters per second. So the initial velocity for both of these is 20.0 meters per second. Initial velocity 20.0 meters per second. Okay. The final velocity, well, it's stopping, so let's go with 0 meters per second. Okay, so coming to a dead stop. Okay, of 0 meters per second. Okay, and then we are given separate times for each of these. So the time for the deployed airbag is 0.75 seconds. The time for the dashboard is 0.025 seconds. Okay, so the acceleration, of course, okay, acceleration is equal to the change in velocity over time. Okay, so we're going to have a different acceleration for each of these because we have a different amount of time for each of those. So our change in acceleration for both of them is the same. So final velocity minus initial velocity is negative 20.0 meters per second. Okay, divided by, in this case, a time of 0.75 seconds. Okay, and then over here, it's still negative 20.0 meters per second, but we're going to divide that by 0.025 seconds. Okay. So our acceleration here, when we calculate it for the airbag, the acceleration is negative 26.7 meters per second squared. And then when we calculate the acceleration for the dashboard, it's negative 800 meters per second squared. Okay, so those are our two accelerations. So the reason that they're negative is because it's pushing us backwards. The car is going forwards. The acceleration is pushing us backwards. So now it's just a matter of the applied force, which is F equals ma. Okay, so force is equal to mass times acceleration. So the mass is 65 kilograms. Okay, that's the same in both of these. So mass is 65 kilograms times, we have different accelerations. So times negative 26.7 meters per second squared. Okay, and then for this one, negative 800 meters per second squared. Okay. So the force acting on us force acting on the passenger by the airbag is about 1,700 newtons backward. Okay, because it's negative backward. Okay, and the force acting on the passenger by the dashboard is approximately 520,000 newtons backward. So you can see that by increasing the amount of time that it takes for something to come to a complete stop, we decrease the net force substantially, which would then save the passenger's life, versus having all of this force applied to them by the dashboard, which means that something very bad